So, good evening, everyone. Welcome to the sixth live session for the course Concrete Technology offered by NPTEL. I am Arshit Agrawal, a PMRF research scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So in today's session, we'll first revisit the last live session that was for week 5 content in a quick recap manner, and then we'll look through the things covered in the week 6 content. So week 6 content that we'll discuss today, it will be in continuation to the previously held discussion of mixture design of concrete, and it is divided into following subsections for today's discussion. So we'll first start with ACI-211 method of mixture design, and then we'll compare all the three standards that we have discussed: IS method, DOE method, and ACI method. Then we'll talk about mixture design based on packing density and rheology. Then we'll talk about batching of concrete and mixing of concrete. In between, I will have some numerical questions related to mixture design and some objective questions also that will challenge your understanding of the concept. And finally, we'll conclude the session and I will address any other queries post discussion. So, last week we concluded the week 5 of the course where we talked about mixture design of concrete. We had a basic overview of mixture design where we talked about different components that are involved in a concrete mixture design. Then we saw how different desired properties of concrete, that is fresh state property, hardened state properties, and durability properties, how they are dependent upon different components of mixture design. We then discussed about target mean strength and characteristic compressive strength. What are these and how are they calculated and how they contribute to the mixture design of concrete. So we aim for characteristic compressive strength, like when we represent concrete grade M25, M30, M35, 25, 30, 35. These are the characteristic compressive strength that we want from our concrete batch. However, we design for target mean strength. When we do the mixture proportioning, we do according to target mean strength, but we aim to achieve the characteristic compressive strength. Then we started discussion on mixture design based on standard provision, where we first looked at overview of IS 456 guidelines, how it provides base for concrete mixture proportioning to achieve desired strength, durability, and workability. We saw different tables and clause present in IS 456, which forms guidelines of mixture design, and especially in this we focused on the durability criteria in detail that was related to table 5 and table 3 of IS code. We then talked about mixture design steps as per IS 10262, which were divided into 9 steps, starting from determining the target strength, then selection of water to cement ratio, then selection of water content, calculation of cementitious content, calculation of total aggregate content, estimation of coarse aggregate and fine aggregate, and then estimation of different aggregate fraction in coarse aggregate, and finally water content correction based on moisture content of aggregate. For this, we solved a numerical also to understand the applications of these steps. Then we talked about mixture design based on DOE method, which is commonly practiced British standard method for mixture design. For this also we talked about different steps of mixture design and saw how the derived relationships and tables that are present in British standard code is used in each step of mixture design. And again for this method also we solved one design numerical. So moving ahead in week 6 content, now after Indian standard method and British standard method, we have ACI method. So ACI method is a widely used procedure for designing concrete mixture, which is developed by American Concrete Institute. Now, before starting with the steps that are involved in the ACA method of mixture designing, we must know some basic information of raw material which we are using and concrete which we need to prepare. So these information include required compressive strength of concrete that should be known to us. Sieve analysis data of fine and coarse aggregate should be known to us. Bulk specific gravity and absorption or moisture content data of aggregate should be known to us. Specific gravity of Portland cement and other cementitious material, if they are used, should be known to us, and relationship between strength and water to cement ratio for available combinations of cement and other cementitious material that are considered should be there for us. So if these information are already available to us, then for the required demand of the concrete mixture design, we can go ahead with the proportioning of different components. So this slide shows the list of steps involved in mixture design as per ACI method. So step one, as usual, is the calculation of target mean strength from known characteristic compressive strength. Step two is the choice of workability level. So if you don't know what slump is required, then based on the concrete component and its need, we can adopt for the appropriate level of workability. Okay, else if we know the slump, then we will know the workability level anyhow. Step 3 is the selection of maximum aggregate size. Unlike other codes where we already have this information of maximum aggregate size, ACI code says selection should be made based on the dimension of concrete member and spacing between the reinforcement bars. Okay, so a little tail of this we'll see in the coming slides. Step 4 is the determination of water to cement ratio, which we will see is done based on the empirical relationship between strength and W by C ratio given in ACI 211 guideline. Step 5 is the determination of amount of mixing water and air. Here, air is an additional parameter to be defined. Like unlike IS code and DOE method, where we assume that there is no air voids in concrete, ACI code provides value of percentage air voids also in concrete for both normal concrete and air entrained concrete. Then step 6 is the determination of cement content. So once we know the water to cement ratio and mixing water, we can determine the cement content. Step 7 is the determination of fine and coarse aggregate fraction, which will be based on the slump and the fineness modulus of sand. And at last, steps 8 is the adjustment in the moisture content of aggregates, similar in the similar manner how we did in the IS code. So let's go in detail for each step now. So step 1 is already known to us. Based on the required characteristic strength and known standard deviation, we can calculate the target mean strength. Now for step 2, that is choice of workability level. If slump is not specified, then an appropriate value of workability level needs to be selected. For this, we have a table in ACI code where we have a range of slump required for different concrete application, as you can see here. Okay, for suppose for example, you want to prepare a reinforced concrete beam. So minimum slump should be 25 mm and maximum slump should be 100 mm as per ACI standard. Now, it is mentioned in the code that we need to aim at the middle of the range that is there. So, one can select for this reinforced concrete beam, we can go with 50 to 75 mm slump as target slump. Okay, so in this way, we read this table which is there in ACI code. Now, step 3 is the selection of maximum aggregate size. Now, this selection is made based on the dimension of concrete member and spacing between the steel reinforcement bar. Commonly, the maximum aggregate size should be largest that is economically available and consistent with the dimension of the structural member. And what IS code says that maximum aggregate size that you're taking should not surpass one fifth of the narrowest dimension between the side of the foam. So suppose these are the foam sides that I have. So this is my narrowest dimension. Okay, this is my longer dimension ly, and this is my shorter dimension lx. Okay, so my maximum aggregate size as per ACI method should not be more than, should always be less than lx by 5. Okay, the narrowest dimension, one fifth of the narrowest dimension. Then it should be less than one third of the depth of the slab. Whatever depth of the slab that we have, the maximum aggregate size should be less than one third of the slab depth. And it should be three-fourth of the minimum clear spacing between individual reinforcement bar, bundles of bar, or pre-tension standard stands. So suppose there are reinforcement here in this beam. Okay, so whatever is the clear distance between two adjacent beams, suppose this is D, so my maximum aggregate size as per ACI code should be less than 3 by 4 of D. Now, why are these limitations here? So that my aggregates don't block the flow of concrete when we pour the concrete inside the formwork. Okay, so that's why there are restrictions that are mentioned on maximum aggregate size in ACI code. Now, in step 4, for determining the W by C ratio, there are two tables that are given in ACI code. Table 3 shows the relationship between average compressive strength and W by C ratio for both non-entrained concrete and air entrained concrete. So, this is my conventional concrete, non-air entrained. Okay. And table 4 shows the limit on maximum W by C ratio to be used for concrete exposed to harsh condition. Okay, so this table that you see here, the similar values are applicated in this figure also. Okay, so based on the required compressive strength, target mean strength of our concrete, we can map the W by C ratio that we need to take, and then we can cross verify that W by C ratio based on the table 4 conditions that are present. Okay, then in step 5, for determining the amount of mixing water and air voids using table 2 in IS 211, we can do this calculation. Okay, so I will give you then understanding of this table by example. Okay, suppose I am preparing a conventional concrete. Okay, and I want a slump in the range of 80 to 100 mm. Okay, and I have 20 mm as my maximum aggregate size. Okay, so code says that we need to take 200 kg per meter cube of water, and we need to assume that there are 2% entrapped air voids inside the concrete. Okay, now suppose I want to prepare a air entrained concrete with the same slump demand and same maximum aggregate size. Okay, and if my condition is extreme for freeze and thaw action, then what code says that I need to take a water content of 180 kg per meter cube, and I need to assume air entrainment of 6%. Okay, now how to fix this 6% in concrete? For this, we will use air entraining admixtures that we discussed a few weeks ago. Okay, so this is how we read this table 2 of IS 2 ACI 211. Then in step 7, so step 6 is the determination of cement content that we can do easily once we know the mixing water and the W by C ratio. Step 7 is the determination of fine and coarse aggregate proportion that we can do from table 5. Okay, and for this we need to know the bulk we need to know the maximum aggregate size, and we need to know the fineness modulus of fine aggregate. Okay, these two data is required for this paper. So like suppose for example I have 20 mm as my maximum nominal aggregate size, and my fineness modulus of sand is 2.8, then I need to take 0.62 fraction of coarse aggregate in total volume of aggregate. Okay, and the remaining will be by fine aggregate. Okay, so once we determine coarse and fine aggregate, then at last we'll do the correction of moisture content and addition of additional water that the aggregates will absorb. And for that, the equations are the same like how we saw in the last session during the discussion of IS code. Okay, so these are all the steps for mixture design as per ACI method. Now we'll just see an application of these steps through a numerical. So just try to read this numerical, understand how you will proceed with this, and then I will share the solution. In the meantime, if you have any doubt regarding ACI method of design, you can discuss or type your query in the chat box. Just think how you will approach this question. Start from step 1 and just try to do on your own. Okay, let's see the solution to this question so that everyone get a clarity how we apply the ACI method of mixture design. So as usual, step 1 is determining the target mean strength. Okay, so as it is given in the question that we need want a characteristic compressive strength of 30 MPa at 28 days. Okay, so and we don't have the data for standard deviation. So suppose I am assuming a standard deviation value of 5 MPa. Okay, so my target mean strength will be nothing but characteristic compressive strength plus 1.35 times standard deviation. So it will come out to be 36.7 MPa. Okay, so this is the strength that I am targeting. Now, step 2 is choice of workability level. Okay, so what it is given to us in the question, we are preparing for a reinforced concrete beam, and slump that is already given to us as 50 mm. Okay, so choice of workability level, it is already given to us 50 mm. However, if suppose slump is not given to us, then using this table 2, we can see for reinforced concrete beam, we generate target a slump of 25 to 100 mm, and the middle range is 50 to 70 mm. But since in question it is given to us that slump requirement is 50 mm, we'll go with 50 mm. Now, step 3 is selection of maximum aggregate size. Now, this selection is done based on the spacing between the reinforcement bars, the dimension of the beam, and the depth of the beam. Okay, so all these things will come once we will do the structural analysis. We will understand how much load is acting on a member, what is the bending moment requirement, and from those only we can get the dimensions of the beam. But just to simplify all those unnecessary calculation for this question, we have directly assumed that the maximum aggregate size required is 20 mm. If it is not given to us in the question, then based on the beam dimension also you can do. Suppose you have been given a beam size of 300 mm cross 500 mm, and depth of beam is 100 mm. Depth of beam is suppose it is 50 mm. Okay, anything you can assume. I am assuming 150 mm. Okay, and clear spacing between reinforcement bars is suppose 25 mm. Okay, so based on this you can do the calculation. So my maximum aggregate size, it should be less than, first condition was 1/5 of the narrowest dimension of beam. So 1/5 of 300 will be 60 mm. Then 1/3 of depth of slab. So 1/3 of depth of slab is 50 mm, and 3/4 of clear spacing of aggregate. So 3 by 4th of 25 mm will be 18.75 mm. Okay, so if such data is given to us, you can go from this. Okay, and you can choose a maximum aggregate size of 12 mm if this is the criteria of beam. But for now, for us, it is given to us that maximum aggregate size to be taken is 20 mm. Okay, so this was just a trial example how we read based on dimension. Okay, now step 4 is determination of W by C ratio. Okay, so what it is given to us in question, we have a non-entrained concrete. Okay, so I will just copy this figure or this table. Okay, so we have a non-air entrained concrete that is given to us in the question, and the mean compressive strength that is required, it is close to 37 MPa. Okay, 36.7 MPa. Okay, so for 40 MPa, you can see the W by C ratio required is 0.43, and for 35 MPa, it is 0.48. Now, for 37 MPa, we can go with the mean of these two values, 0.43 and 0.48. Okay, so based on this, let's take W by C ratio as 0.45. Okay, and same thing you can do from the graph also, but for now I have done from the table. So I have fixed the W by C ratio as 0.45. Now step 5 is determination of total mixing water and air voids. Okay, so again I know slump demand is 50 mm, maximum aggregate size is 20 mm, and we have non air entrained concrete. Okay, so based on the table that is given, okay, so based on this table you can see for 50 mm slump demand, 20 mm maximum aggregate size, my free water content is 185 kg per meter cube, and my air entrapped air content is 2%. Okay, so I will take water content is equal to 185 kg per meter cube, and air void content is 2%. Okay, now step 6, determination of cement content. Okay, so we know the W by C ratio and we know the total mixing water. The cement con- content will be water content divided by W by C ratio, so it will come out to be 411 kg per meter cube. Then after determination of cement content, step 7 is determination of coarse and fine aggregates proportion. Okay, so we have maximum aggregate size of 20 mm, and fineness modulus of sand is given to us as 2.80. Okay, so based on the table that is given to us for 2.80 and 20 mm, coarse aggregate fraction is 0.62. So my coarse aggregate fraction is 0.62 of total volume. So, and fine aggregate fraction is 0.38. Okay, so first we need to find the volume of total aggregates. Okay, so what is the volume of total aggregate? It is nothing but 1 minus 0.02, which is air voids, minus 411 divided by 1.3.15 into 1000, that is the volume of cement, and 185 divided by 1000, that is the volume of water. Okay, so it will come out to be 0.665. Now coarse aggregate fraction in this is 0.62 times 0.665, so that will be, so if I calculate the weight, okay, so 0.62 times 0.665 times density, so 2.68 into 1000, so it will come out to be 1105 kg per meter cube, and fine aggregate will be 0.38 times 0.665 into 2.65 as per the specific gravity data given to us in question, times 1000, so it will come out to be 669.6 kg per meter cube. Okay, so this is how we determine all the proportions that we require. Now after this we will do the moisture correction. Okay, for that you know the steps, okay, how that correction is done. So in this question you have been given the absorption air content of aggregate and the moisture capacity of aggregate. Okay, so dry if this is the dry state of aggregate, This is the in situ state of aggregate, and this is the moist SSD state of aggregate. So from this to this, for coarse aggregate, water absorption capacity is 2%. Fine aggregate absorption water absorption capacity is 2%. For coarse it is 1, for fine it is 2. And between these two, you have been given for coarse aggregate is 0.5%, and for fine aggregate it is 1%. So knowing this, you can find how much volume of water you need to add to convert the in situ aggregate into SSD, and how much correction in aggregate weight you need to do, okay, based on the equations that I discussed in the last live session. Okay, I hope everyone are clear with this question. Any doubts in any steps?
No, sir. Go ahead.
Okay, now since we have discussed all three commonly practiced mixture design codes, that is IS method, DOE method, and ACI method, let's just have a basic comparison between them, an overview of how they compare against each other. So there are different design aspects that I have listed here in the first column, and what different design method says about that design aspect is written in the subsequent columns. Okay, so for target mean strength, all three code, they work on the similar rule, which calculates the target mean strength based on strength requirement and standard deviation. Okay. Now for fixing the W by C ratio, IS method opts for strength versus W by C ratio curve and durability requirement based on exposure condition severity. Dewey method, again it uses strength and workability requirement. Okay, in IS method we didn't talk about workability requirement for fixing the W by C ratio. Okay, and in ACI method we have tables for strength and exposure condition and how they affect the W by C ratio. Then for water content, the IS method depends upon slump, exposure condition, and workability requirements. Slump and the workability is the same thing. DOE method takes into account workability and aggregate size, and ACI method takes into account slump, air content, and maximum aggregate size. Okay. For cement content, once we know W by C ratio in water content, we calculate the cement content. Okay, and we check it based on durability limits. Okay. For coarse aggregate content, IS method says that we need to know the grading zone of fine aggregate, whether it belongs to zone 1, zone 2, zone 3, or zone 4, and we need to know the maximum aggregate size of coarse aggregate. DOE method, it uses grading limits in wet concrete density to calculate the coarse aggregate content, and ACA method uses the information of maximum aggregate size and fineness modulus of fine aggregate to calculate the coarse aggregate content. Then fine aggregate content we get once we know the coarse aggregate content and total aggregate content. Okay, so these are the basic difference between IS method, a DOE method, and a ACA method of mixture design. Okay, almost all rules are the same. There is a little difference in the three method. And what is the best usage of all the three methods? It depends upon the geographical location. So IS method, it is best used for Indian projects where local condition and material must be considered. DOE method, it is used for high strength concrete with optimized cement content, and it is mainly used in UK and Europe. Okay, while ACE method, it is used as for general concrete design, which includes air and train concrete also, which is widely opted in US and international project. Why ACA method considers air entrained concrete? Because of the geographical location where demand for where risk of freeze thaw action is much more severe compared to locations in UK, Europe, or India. Okay, so that's why they have a separate section which talks about air entrained concrete. Now, what if we take same raw material information and prepare a concrete mixture from the three standards for the same problem? So suppose I have this problem statement where I need to design a concrete mix for a compressive strength of 25 MPa for at 28 days, and I have been given I need to use maximum aggregate size of 20 mm, slump 75 mm, air content is given to us, specific gravity of cement, coarse aggregate and fine aggregate is given, and moisture content information, water absorption capacity information, and fineness modulus of sand is given to us. Suppose we know all the information that are required. Okay, now these are just some limited information that I have mentioned. Other required information one may assume at some fixed entity. Okay, so this is some exercise for everyone. Try to design concrete mixture using all three standard. Okay, for the same uh, uh, pr- basic details. Okay, for now, suppose designing is done and I have the proportion of cement, water, aggregate, and W by C ratio that I have shown in this table below. So, can anyone explain me the observed differences in the obtained mixture design? Like what you observe. Okay, suppose for this example, you get this mixture proportioning from three method. Now, what you are able to observe? Can anyone explain me based on the per meter cube content of different proportion? What is your takeaway? Just give it a try. Just think what you are understanding from the mixture design.
Water cement ratio.
Yeah, and like what do you understand by the difference? You can see that okay, these values are different. Why they are different?
Maybe in the IS 456, the water cement ratio is controlled. If more than 0.45, we cannot use that. Is reduced for that. For that only, the cement content is more for the M20. I think.
Okay, that's one point. So in W by C ratio, you can see IS code is based on a conservative approach. Okay, the maximum W by C ratio that is there based on durability condition that has been taken, while DOE method, as we talked one slide ago, it is mainly designed for higher strength. It mainly optimizes concrete proportions for higher mechanical properties, and that's why you can see the water to cement ratio that is coming, it is the lowest among all the three. Okay, while ACI method, it is less conservative compared to the other two when we talk about what the W by C ratio. Any other difference that anyone can spot? Any other major difference? One can see the difference in the cement content also. ACI method has less cement content. Okay, however, more coarse aggregate proportion compared to a DOE method. Okay, while IS method, it requires high cement for durability and a good proportion of coarse aggregate also in its composition. Okay, so each method that you will see here, it has its own advantage and limitations, and whole proportioning thing based on the durability needs, the regional demand, and the cost considerations also. Okay, so there will be difference in mixture design when you will do for the same problem. There can be different mixture proportioning that can be present. However, you need to see the geography of your project, and based on that you need to finalize one mixture design. I hope this mixture design part is clear to everyone based on different standard provisions.
Yes. Yes.
So, till now, we have discussed all conventional forms of mixture design, which were based on one common aspect, strength and workability, defined as a function of W by C ratio. Now, we'll look at an advanced form of mixture design that is based on packing density and rheology. Okay, so a mixture design of concrete that considers packing density and rheology is essentially for optimizing workability, reducing porosity, and improving mechanical properties. Now, How such mixture design work? Okay, so we know that concrete has a particulate nature. That means that it is composed of particles or materials of different sizes. So in fresh concrete, in fresh state, the wet cement paste and aggregate system forms the concrete. Now, for enhancing both strength and workability, we will enhance the packing density of aggregate system, which will minimize the interstitial voids. And then by optimizing the rheology of the cement paste in terms of yield strength and viscosity, we can optimize the flow behavior of fresh concrete, which will control the workability, pumpability, and segregation resistance. Therefore, in this way, we are optimizing both strength and workability of a concrete. Now, unlike other methods, there is no defined codal provision or something for such mixture design. Rather, it is more based on laboratory trials and experiments, and thus such mixture design is often called as advanced mixture design and are commonly used to prepare high performance concrete like UHPC, ultra high performance concrete, which have strength of more than 100 MPa. Okay, so such concrete, it works on the basis of optimizing the packing density and then optimizing the rheology of the paste. So the core of such mixture design is based on three steps. Step one is optimizing the aggregate combination using the concept of particle packing. Second step is ensuring that cement content is just enough to provide required workability. And third step is to optimize the paste composition for best flow for both particle packing and rheology. Okay, so we'll see these steps one by one. Now, particle packing is something we have already discussed in detail in our previous section. So, I can just try to simplify this concept in an easy way again. We can say that instead of using a single sized aggregate and relying on cement paste to fill the voids between the aggregate and make concrete compact, a system of multi sized aggregate ensures that larger voids between coarse aggregate are filled by subsequently smaller size of aggregates, which are known as fine aggregates. So by optimizing the proportion of uh, uh, particle packing, that is the proportion of coarse and fine aggregate, we can minimize the voids that are present in the aggregate skeleton, which will either reduce the paste demand or which can give us more workable concrete for the paste, same paste content. The same thing you can see it is written in this statement also. A well graded combination of fine and coarse aggregate maximizes the packing density. Okay, so particle packing of aggregate is done for optimized gradation. Okay, so we have seen that like well graded combination of coarse and fine aggregates, they will give maximum packing density and minimum air volts. Okay, and same thing you can see in this image also. Coarse aggregate, fine aggregate, and when they are optimized, you can see how much slower is the air void content in this optimized gradation compared to an just singly sized aggregate fractions. Okay, now how we achieve optimized packing? So first step is the selection of range of particle size which are available to us. Okay, suppose we have to us it is available, 20 is available to us, 10 is available to us, 4.75 is available to us. So in this way we first see what all range of particle size are available, aggregate size are available to us. Then we determine the packing density. For this, there are two theories which are present. First is the discrete particle approach, okay, which was first proposed by an author named Furness in 1931. So this approach says that densest packing occurs when fine aggregate exactly fills the void within the larger particles. Okay, so this is the statement that was given by the scientist named Furness. Okay, densest particle packing occurs when fine aggregate will exactly fill the voids between the larger particles. However, this approach has two major limitations. Okay, as the size of fine aggregate approaches the size of coarse aggregate, for there are two problems that comes in the interaction of these aggregates. First is the wall effect, which is due to increased air voids near coarse particles or other boundary. Okay, so this is one effect. Okay, and second is the loosening effect, where due to increased the void, where there is an increased void in between aggregate and fine particles start to disrupt the packing of coarse particle. Okay, so in wall effect you can see when there is a big suppose we have a foam work. Okay, and these are the walls of the foam work. So when we try to optimize the packing of aggregates, there can be portions where near the foam work there will be big voids that are created due to insufficient packing near the edges. Okay, so that effect is known as wall effect. Okay, and loosening effect comes when we have too much of fine aggregate in the system in such a way that they are, instead of decreasing the void content between the coarse aggregate, they are disrupting the coarse aggregate from packing efficiently with each other. So these two limitations were identified for discrete approach. Okay, so there was one more theory that was there instead of discrete approach, and that theory was known as continuous approach. Okay, and this was proposed by authors Anderson and Anderson, okay, in 1930. So this approach says that densest packing is achieved by assuming that smaller particles are infinitely small. Okay, this means that void space between coarse aggregates shall be continuously filled by its finer aggregate size, like you can see in this image. Okay, so voids between this size of aggregate will be filled by this aggregate, then voids between these size of aggregates will be filled by the further smaller aggregate, and so on till the finest of aggregate available. Okay, so this is known as continuous approach. Okay, now once we determine the packing density of a system, okay, the next step is to minimize the void content, for which packing density needs to be optimized, and it is optimized by adjusting the proportion of different aggregate sizes to get the maximum packing, and this is done using this equation. Okay, that is given to us. Okay, so the equation says that packing density is equal to mass upon specific gravity of that corresponding aggregate type, and summation of this divided by volume of container. So knowing the volume of container and for different mass of different aggregate type and specific gravity of aggregate types, we can optimize the packing density of an aggregate fraction that is available to us. Once you optimize the packing density, void content we can calculate by 1 minus packing density. So if my packing density is optimized, my void content will be minimum. Okay, and once we have optimized, minimized the void content, the final step is optimizing the paste volume to be more than the void percent, so that we can ensure required strength and workability. Okay, so suppose my void percent is 5%. Okay, so for 1 meter cube, if I know 5% is my void content, then the paste volume that I am taking, it should be more than 5%. Okay, so that it can efficiently pack all the aggregates, and it can also provide the level of workability required from the concrete. Okay, so these are the basic steps that we need to follow for designing, optimizing the packing density, and optimizing the paste content volume. So this figure shows a simple contour map for a ternary aggregate system. Okay, so we have 20 aggregate, we have 12.5 aggregate, and we have river sand. Okay, now how to read this figure? So suppose you know that you have 30%, suppose you are taking a combination of 30% 20 aggregate, then 30% of 12 point 30% of river sand, and 40% of 12.5 aggregate. Okay, so what we'll do, this is my scale for, where is my- this is my scale for 20 aggregate. Okay, so here I will take the mark of 30 and I will draw one line. from the point, like this. Then for sand, again I have the mark for 30 mm, and I will draw a line for through that point. Okay. And for 12.5 mm, I have a mark for 40 mm, through which I will draw one line. Now the point at which these three interact will give me the packing density of the system. Okay, and these line that you see here, the red line, the green line, the black line, these are all the packing density volume for different combinations of these three aggregate fractions. So right now my point is lying somewhere between, somewhere very close to this red line mark. So I can say that the packing density of these three combination for these 3%, it will be 0.64. Now, if I want to optimize, I can just change the proportion of aggregate and I can see whether I can achieve a higher packing density or not. Okay, so that can be done by optimizing the proportion. Okay, so this is a contour map and how we read that map. Now, based on this understanding of packing density concept, just try to answer these three simple questions. And in the meantime, if anyone has any doubt, you can ask. Just tell me the answer for question number three. So the question says the packing density of a granular material is influenced by which of the following factor: particle size, particle shape, moisture content, and compaction method. So what will be the correct answer?
Particle size.
Just think about all the options. I have given you four options here. Which option will be correct? There can be multiple correct options for this question. Just think about all the four options. Do they influence the packing density of a granular material? What all options do you think are affecting
B
the packing
1,
density?
2, and 3.
1, 2, and 3. Okay. Can anyone tell me how 3 affects the packing density? 1 and 2 are very clear. Okay. Particle size distribution, a well graded mix has higher packing density than a poor graded mixture. And particle shape and texture also we know. Angular or rough textured particles, they can reduce the packing density compared to round and smooth particle. Okay, compared to round aggregates, an angular aggregate will have a better packing density. But how 3 and how 4? How moisture content influences the packing density? Can anyone tell me?
If more moisture means segregation going to happen.
What? Can you repeat?
Water contains more means segregation and going to happen.
No, moisture content of aggregate we are talking here, not in concrete. So basically, the correct answer for this question is C. Moisture content also influences the packing density. How? Because if there's some moisture present on the aggregate, it can reduce the friction between the aggregates. Okay. And if there is excessive moisture present, it can lead to separation between aggregates also. Okay, because of water present between the aggregates. Okay, excess of water on the surface of aggregate. So moisture content also has an influence on the packing. Okay, it affects the friction, okay, between aggregates, and that friction can govern how aggregates are slipping above each other and how well they are trying to compact each other. And compaction method, as you know, it will influence the packing density. So if I will do vibration compaction, it will reduce the air voids. Okay, it will force the aggregate to push towards each other and close the gaps. However, if I don't compact my concrete, you will see there will be lumps and honeycombing that are there in the concrete. Okay, so compaction method also influences the packing density. Question number 4. For self compacting concrete, why is achieving higher packing density important? Can anyone tell me the answer? A smaller moisture content basically decreases the friction between the aggregates. So they will try to slide over each other and pack efficiently when some compaction is given to them. Okay, that is a reason. But if there is excess of moisture, then it will be a problem. Instead of friction supporting their reduced friction, helping them to compact, it can lead to separation also if there is excess of lubrication. Okay. For question number 4, yes, the correct answer is A. Okay, so what happens when for why high packing density is crucial for a self compacting concrete? It is to reduce the need for excessive paste. Okay, and if we'll reduce the needs of excess paste, it will lead to better stability, lower shrinkage, and improved durability of a concrete. Plus, it minimizes segregation issues in concrete, and which ensures that there is a uniform mix without requirement of any vibration. Okay, so that is the advantage of achieving high packing density in a self compacting concrete. Okay, so with the reduced paste content, we will have good flowability in the system, and there won't be any risk of segregation or bleeding. Okay, for a self compacting concrete. Question number 5. In a ternary mixture containing cement, fly ash, and silica fume, which component primarily enhances the packing density. So suppose I am calculating packing density of cement. Okay, we know fly ash, silica fume, and cement OPC all have different size range. So for them also we can optimize packing density just the way we do for aggregates. Okay, so in this ternary system, which component has the major influence on packing density? uh, and whatever your answer you are giving, give me the reason also why.
Silica fits is more fine, surface area is more.
Yes, silica fume, why it is correct?
Uh, Fineness, more fineness, and surface areas more.
Yes, the correct yes, that is the correct explanation. So we know silicon fume consists of ultra fine particles. Okay, and these ultra fine particles, they can fill the macro voids and micro voids between cement and fly ash particles. Okay, which can increase the overall packing density of the system. Okay, so in general, the proportion of finest of particle, they have more influence on packing density than the proportion of coarse particles. Okay, and if you want to do that in practice, so understand this in practice, just redo this contour map. Okay, just think of different combinations of different proportions of sand, 20 mm and 12.5 mm aggregates, and check what packing density you're getting. Okay, and how it is getting influenced due to different aggregate proportion. Okay, so you'll see fine aggregate proportion, they play a critical role in the packing density. Any doubt in these three questions? Yeah. Now, after packing density, we have rheology. Okay, so rheology is a fundamental property that governs the flow behavior of fresh concrete. And for understanding rheology, it is crucial because it directly affects the workability, pumpability, and segregation resistance of concrete. Also, it helps us to determine how concrete behaves before it hardens. Okay, which is important to ensure that it can be placed, compacted, and finished properly. Okay, now when we talk about rheology, there are three main parameters that define the rheological behavior of concrete. Okay, first is the yield stress, which represents the resistance to initial movement. Okay, and yield stress is like the minimum stress that is required to initiate the flow. Okay, a concrete mix which has high yield stress, it will be stiff and difficult to work with, while a concrete mix which has low yield stress, it may lead to segregation. Okay, so yield stress is one of the parameter of rheology. Okay, resistance to initial movement. Second is the plastic viscosity, that is resistance to flow once material has started moving. Okay, so it determines how easily concrete will flow under an applied stress. Okay, suppose I have a concrete batch, okay, and I have provided it sufficient yield stress for it to initiate the flow. Now, how much it is resisting to flow after an application of stress, it is given by the term plastic viscosity. Okay, a mix that has high plastic viscosity, it will be sluggish, while a low plastic viscosity mix can cause excessive bleeding and segregation. Okay, and third is the thixotropy, okay, which refers to time dependent stiffening behavior of concrete. It means that after resting, concrete tends to become stiff, but it regains flowability when remixed. Okay, so this property is essential for maintaining the shape while ensuring the ease in concrete placement. Okay, so these three are the critical properties when we talk about rheology of a concrete. Okay, yield stress, plastic viscosity, and thixotropy. Now, why rheology is important? Because it tells us about the fresh state behavior of concrete under different conditions. Okay, so during compaction by vibration, fresh concrete must yield easily to flow and take the shape of the formwork. It should maintain uniformity and cohesiveness, ensuring that segregation does not occur. And if if we don't control rheological properties properly, then we will have issues like poor finishing, uh, honeycombing, and excessive bleeding in concrete. Okay, that is not desired to us. Now, to study the rheological behavior of concrete, we analyze the shear stress versus shear strain profile. And this helps us to understand how material transitions from a rested state to a flowing state under pressure. Okay, so by optimizing rheology, we can design a concrete mix which is easy to place, pump, and finish. Now, let's look how the shear stress versus shear strain profile relate in different materials. So, as shown in the figure, Newtonian fluid, they exhibit a linear relationship between shear stress and strain or shear rate, meaning that flow instant they flow instantaneously under any applied stress. Okay, so at any amount of stress that I apply, the shear rate there is a shear rate means there is a strain in the system. That means that there is some flow in the system. Okay, however, the such idealized behavior, okay, it is good approximation for a self compacting concrete, okay, which compacts on its own, which doesn't require any force, okay, for movement. Okay, however, for fresh concrete, we generally assume that it behaves like a Bingham plastic, where flow only initiates when a certain yield stress is applied to the concrete. Okay, so mathematically for liquids, shear stress and strain rate, it is related by this equation. Tau is equal to mu times del y by del t. So either tau is the shear stress, del y by del t is the shear rate, and mu is the coefficient of viscosity. Okay, plastic viscosity. I guess I guess there was some disruption in my network. Can anyone tell me at what point it occurred? I was not able to see that disruption. Hello, am I audible?
Yes, sir, audible.
Can anyone tell me at what point uh, the network went off? On which slide it went off?
Just 2 seconds only.
Okay, so I was on discussing the rheology of concrete only, right?
Yeah, yes, yes.
Okay. So in rheology, we saw that for self-compacting concrete, it follows a behavior of a Newtonian fluid, but normal conventional concrete, they follow a behavior of Bingham plastic, where a certain yield stress is required to initiate the flow. Now, how shear stress and shear rate are related? They are related by this simple equation. Okay, where mu is the viscosity of the material. Now in concrete, different rheological model helps us to describe its behavior. The simplest model is the Newtonian fluid, but for practical application we use Bingham model. Okay, as it effectively captures the yield stress and plastic viscosity, which are key to understand the concrete flow and its consolidation performance or its compactability. Okay, how well it can compact. Okay, so this is about the rheological parameter. Okay, now a simplest of understanding of viscosity and how it affects the concrete flow, which we can see in this figure. So in the first case, we have a high viscosity concrete. We can see it takes times to collapse. Okay, so you can see this is the initial state of concrete. I placed a slump cone and I poured the concrete inside the slump cone and I removed the slump cone. So at 0 second, it was retaining the shape. After 5 seconds, there's certain drop in the slump, and after 10 seconds, it completely collapsed. However, for a low viscosity concrete, which doesn't have much viscous nature, as soon as I will remove the slump cone, you can see within 5 seconds it has completely collapsed. Okay, so a high viscosity concrete, you can see it takes times to collapse because it is viscous in nature. However, a low viscosity concrete, it collapse sudden because it is less viscous. So it defines the resistance of concrete against flow once the motion has been initiated. So here the motion was initiated due to the gravity effect that is occurring on the concrete, and this gravity effect must be larger than the yield stress of concrete. That's why the flow got initiated. However, due to high viscosity here, there was higher resistance to flow. That's why it collapsed took time, and here due to low viscosity the resistance to flow was lower, so it collapsed instantaneously. Okay, now I need to check the connection again and again. Yeah, it is connected. Now let's see how rheology defines my concrete. Okay, so in the first figure we can see we have yield stress on y-axis and we have viscosity on x-axis. Okay, so suppose I have a reference case for which I know the yield stress and I know the viscosity. Okay, so compared to this control, if my concrete is more viscous, then for the same yield stress I will have higher viscosity, okay, in concrete. Compared to reference, if my concrete mix is stiffer or we can say less workable, then for the same viscosity my yield stress will increase. Okay, and compared to reference, if my concrete is wet or we can say it is more workable, then both yield stress and plastic viscosity will be lower. Okay. Now, the second figure shows the similar understanding where effect of paste volume, water, and addition of fly ash and silica fume and SP is showed to affect the rheological behavior of concrete. So compared to reference, if I have less water, then both my yield stress and plastic viscosity it will increase. However, if I have more water, both yield stress and plastic viscosity will decrease. If I have more paste, then yield stress will decrease, but plastic viscosity may increase. However, if I have less paste, my plastic viscosity will decrease, but yield stress will increase. Similarly, for SP, you can see with the addition of SP, yield stress decreases for the same plastic viscosity. And for when there is more air voids inside concrete, the plastic viscosity tends to decrease for the similar yield stress. And in silica fume, the yield stress it may remain the same, but the plastic viscosity increases as silica fume causes stiffening in the concrete, which decreases the viscosity of the concrete. Okay, so in this way, one can understand the effect of different parameters and how they affect the rheological properties of a concrete. Now, when we talk about the pace system, it is not just the binder proportion or W by C ratio, but we also need to take care of the of the superplasticizer dosage. Okay, so for cementitious material combination, it can be optimized based on particle packing. Okay, so selection of paste volume it determines the cementitious material combination and chemical admixture dosage for a required W by C ratio, and this combination can be optimized based on particle packing. However, SP dosage, so we know we have seen this thing in the few slides ago. Okay, the similar way how we have contour map for aggregate, we can have a contour map for cement also for different size of cement, where we can optimize the packing density of different cementitious material combination. However, SP dosage is optimized based on the concept of rheology by measuring the fundamental properties that are yield stress and plastic viscosity. And these parameters for SP are measured by two empirical test method. One is the Marsh cone test, which measures the plastic viscosity, and second is the mini slump test, which measures the yield stress. Okay, so Marsh cone test you can see here. Okay, it measures the plastic viscosity. So in this, what we do, there is a cone in which we pour the cement paste having some SP dosage. Okay, up till a certain mark, and then we release this knob here and we see at what rate it is filling the this graduated marked cylinder. Okay, then based on the time of filling to a certain volume, we get an idea what is the viscosity of the system. Okay, so this is March cone test. Then in mini slump test, it is like a miniature version of slump cone. So in this, we pour the cement paste plus SP system. We level it from the top. We do a little compaction with hammering here and here, and we raise the slump cone and we check the spread of the paste. Based on the spread of the paste, we get an idea of the yield stress of the system. So for optimizing SP dosage, we use these two tests. Okay, now based on that understanding of rheology of concrete, just try to answer these three simple questions, and in the meantime, if you have any doubt regarding the concept, you can ask. So what will be the answer for question number 6? Can anyone tell me? In a concrete mix, what is the primary cause of an increase in yield stress among the following four options? Which option will increase the yield stress in concrete? Any guesses? Can anyone give a try? What can be the correct option? Anyone else wants to try? Can you tell me the reason why option B is correct? Okay, correct option is B only. Okay, so what happens? Higher coarse aggregate content, it increases the friction and the interparticle resistance in concrete. Okay, and this leads to making the concrete. It makes concrete harder to mix and to start flowing. Okay, so that's why we say what increases the yield strength, a higher coarse aggregate content can increase the yield strength, yield stress. Question number 7, a self-compacting concrete mix should ideally have which rheological characteristics? Okay, for a self-compacting concrete, which rheological properties are ideal? Can anyone tell me based on your understanding about yield stress and plastic viscosity? It is not just because of density, it is more because of the particle interparticle resistance and internal friction between the aggregates, so they will increase the demand for yield stress. Okay, more paste content and less aggregate content, it will make concrete more flowable, so it will decrease the yield stress. However, more aggregate content, it will increase the yield stress because there will be friction between particles. They will try to resist the flow, so overall for a concrete it will increase the yield stress. Tell me the answer for question number 7. What will be the correct option? Okay, I will tell you the answer. For seventh question, the correct option will be C. Okay, so a self-compacting concrete should easily flow without segregation or without any excessive bleeding. That is known to us. And it needs a lower yield state to initiate the flow and filling the foam work. So that we saw from the Newtonian fluid graph. And however, it should have moderate plastic viscosity and not low plastic viscosity. Why? Because it should be able to maintain cohesion and prevent segregation. So with higher fluidity doesn't mean that there can be segregation in the system. There should not be segregation, like cement and aggregate should flow together, and for that we need a moderate plastic viscosity where there is cohesion that is maintained and there is no segregation in the system. Now, question number 8. Which of the following best describes the effect of viscosity modifying admixture in concrete? What a viscosity modifying admixture does in concrete? Can anyone tell me the answer for question number 8? Any guesses?
B, sir.
No, B is not the right answer. Just think about what is the role of a viscosity modifying admixture. Okay, since you don't know much about a viscosity modifying admixture, so I will tell you the answer right now. The correct answer is C. Okay, so what happens? A viscosity modifying admixture, it increases the plastic viscosity of a system without significantly affecting the yield stress. And such admixtures, they are used in self-compacting concrete. Okay, because in self-compacting concrete we have a very high W by C ratio, we have a very high flowability, and in such high flowability there is higher chances of segregation and bleeding in concrete because of low viscosity in concrete. So to increase the viscosity of concrete, to reduce the chances of segregation and bleeding, we add viscosity modifying admixture. Okay, they increase the viscosity of a self compacting concrete, which prevents the segregation. Okay, and ensures that there is uniform mix flowing in the formwork. Okay, so this understanding, now it will be clear to you when after you understand the action of the rheology of concrete, what yield stress, what plastic viscosity means to concrete flow. I hope all three questions are clear to everyone. Now, till date, we have talked about individual materials, their properties, and how each raw material can be engineered to form a concrete of a specific performance requirement. And then, based on design standards, we estimated the proportion of different raw materials for a required strength and durability condition of concrete. But once the designing is done and once trials are conducted to validate the design, the next step is to actually cast concrete on field. And for this, the first step is the batching of raw materials. Okay, so batching is the process of measuring the specific quantities of ingredients of concrete like cement, aggregate, water, and admixture in correct proportion as determined during the mixture design of concrete. Now, why do we require batching? Because from mixture proportion we get the quantity of material per meter cube of concrete. Okay. However, may actually on site we may require more quantity of concrete, or my mixture may not be capable of mixing 1 meter cube of concrete. Okay. So I need to take all the ingredient as per the batch capacity. And now this and for this batching of concrete comes into action. Okay. Now, batching can be done in two ways. Either there can be way batching and there can be volumetric batching. Okay. So, in volumetric batching, we use measuring boxes, buckets, and volumetric containers to batch the different quantities of material. However, this is less precise and it may lead in variation in mixture proportion. Okay, so that's why such volumetric batching, it is suitable only for small scale projects and less critical works. On the other hand, weigh batching, which is recommended as per IS 456, it measures ingredients by weights using weighing scale or load cell, and it is more accurate and ensures consistency in mixture proportioning, and it is used for large scale projects and RMCs. Okay, so once we know the capacity of the mixture, we can weigh the different ingredients as per the batch size. Now, one of the image here shows the volumetric batching using the measurement box, as you can see here. Okay, so what do? We take the components, say aggregate, we pour it in the fixed volume box till the top and we level the top. Okay, however, there is a problem here, and that problem is compaction. Different degree of compaction may lead to different quantities of aggregate poured in the measuring box, okay, which is undesirable. Then there is a box tool, okay, in which is used for way batching of different components. Okay, and it is mainly used for aggregate batching. So you can see there are two openings here, and through these two openings aggregates are poured, and the particular weight of aggregates is then measured in the for the concrete mix. Okay, in the top image you can see a batching plant on site. So there are different big cylindrical silos that you can see. These silos, they store the cement and other chemical admixtures like fly ash and slag. Then there are quarries also which are present. Okay, so these quarries, they store the aggregates of different size, and this is separated by wall. Then there will be some water tanker also for storing water, and there will be some other silos also where chemical admixtures are stored. And at the top, there is a control unit which takes cares of weigh batching and proportioning. So control unit, it collects different raw materials in specific proportion from unit storage, from different unit storage, and it pour it into the concrete mixer, which after mixing is ready to be poured inside. Okay, so you can see from aggregate we get the aggregates in different proportion. Water is there, cement is there from cement silos, then chemical admixtures are there. They are all mixed in a mixer. Once mixing is done, it is taken to the site using a transit mixer truck or through conveyor belt. Okay, based on the distance between the mixing station and the pouring station. Now, often when we do wave batching, there are chances to record error in the measurement. So, up to what extent this error can be neglected is it is known as tolerance. Okay, so you can see as per IS 45144952, for individual batcher, the following tolerance shall be applied based on the requirement of material. Okay, so for cement and cementitious material, 1% tolerance is allowed. For sand and aggregate, 2% tolerance is allowed. For water, 1% tolerance is allowed. And for chemical and for admixtures, chemical and mineral admixtures, 3% tolerance is allowed. Okay, so as per IS 14952 clause 6.3 1.3, the minimum weight of any material weighed to which above tolerance shall determined by the following formula. So W is equal to zero point 0.3 times R by T, where W is the minimum weight, R is the scale capacity, and T is the tolerance. Okay, so I will explain you this formula by an example. Okay, so let's assume we have a weighing scale which has a capacity of 100,000 kg. Okay, and I am weighing aggregates on this weighing scale. So I have a tolerance of 2%. So minimum weight of a material that I should take such so that this tolerant limit is valid, it will be given by zero point 0.3 times 1000 divided by 2. That will come out to be 150 kg. So for this scale, a minimum weight of aggregate that I should weigh should be more than 150 kg. If the weight is lower than 150 kg, then my accuracy of weighing may not be reliable as per standard. Okay, so this is the concept of tolerance. Now, after batching is done, the next step is mixing of concrete. Okay, so for mixing concrete, there are two different types of concrete mixers. There is then these are categorized in two domains: batch mixer and continuous mixer. Okay, so batch mixer again has two types. There is pan type mixer and there is drum type mixer. And in drum type mixer, we have tilting drum, non-tilting drum, and reversible drum. So you'll see all these types of mixer through images in the next slide. Okay. Now, what do you mean by batch mixer? So, batch mixer, after pouring all the materials into a pan or a drum, it mixes all those material for some time and it finally discharges. And this process is repeated until the required quantity of concrete mix is obtained. So, in batch mixer, what we do, we pour a concrete batch. Okay, we mix it and we take it to site, and then we pour again one more concrete batch, we mix it, we take it to site, and this process is repeated until the required amount of concrete mix is obtained. While in a continuous mixer, loading, mixing, and discharging of mix is done continuously until the work is completed or work break occurs. And it is used for large scale projects like dam, bridges, construction of high rise building. So, in this, what happens? Materials is poured from the top, mixing is going on, and material is taken away, okay, from the mixer, and this process is continuous. Okay, it continuously happens until the work is completed or there is some work break taken. So let's see these mixers through images. So the first case is the drum type mixer, where the concrete ingredients are mixed in a drum which is actually a double conical frustum shape. Okay, so you can see a drum type mixer here. Okay, so in this drum, concrete is mixed. Okay, so drum type mixer, this is also a drum type mixer, this is also a drum type mixer. Okay, so in this drum type mixer, there are three categories. There is tilting drum, there is non-tilting drum, and there is reversible drum. Okay, so in tilting drum, the drum will discharge concrete by tilting downward, and it has a rapid ability to discharge and then is often used for large scale projects. Okay, so the tilting drum mixer, it is often used for low workable concrete, okay, which has larger particle size greater than 7.5 mm, because for more workable concrete it can encounter the problem of segregation. Okay, and then in the the image you can see the procedure of this. Okay, so we are pouring the material, okay, in this position. Then while mixing it is tilted a little, and while discharging the drum is tilted downwards, so all material comes out. However, if there is high workability in the material, then what will happen? The aggregates won't flow, the paste will flow. Okay, that's why we use tilting drum mixer for low workable concrete. I hope I am connected. Yes. Then after tilting drum mixer, there is non-tilting drum mixer, where mixers are not allowed to tilt, but the drum rotates along its horizontal axis. And for discharge, there is a blade that is arranged in inclined position that will receive the concrete mix. Okay, so you can see here in this image. Okay, so mixing is done continuously, and there are discharge driver mechanism. Okay, so from here concrete is charged, mixing is done, and then concrete is pushed out from the other end. Okay, so there are two ends, one is for pouring and one is for collecting the material after mix. Okay, here rapid discharge of concrete is not possible. Okay, and also larger size aggregates are not discharged easily. Okay, so this side, the such mixer, they are used for small scale projects. Then there is rotating drum mixer. Okay, this is also non-tilting type drum mixer. You can see from the top we have poured material, mixing is done, then we remove the shaft and we take the material out. Okay, so this is also non-tilting type drum mixer. Okay, then there is rotating drum mixer, okay, that you can see here. Okay, so it is similar to non-tilting mixer. It has two opening, one for pouring and one for discharge. However, unlike other drum mixer, here the drum rotates in two direction. Okay, it takes the material in one direction and in opposite direction it does the discharging. Okay, so for suppose in clockwise direction it is doing the mixing, then in anti-clockwise direction it will do the discharge. Okay, so these are drum type mixers. Then after drum type mixers, we have pan type mixer that you can see here. Okay, so it consists of a circular pan in which concrete is mixed, and mixing is done using these blades which are present inside the mixer. Okay, so so there can be two types of pan mixer. One where only pan is constant and only blades are rotating about its vertical pan, vertical axis of the pan, and in the other case pan mixer is also pan mixer is rotating while the blade is in constant position. Okay, so in both the cases, what is happening? Concrete is getting mixed due to the movement. Okay, now there are some special blades in this pan mixer. One is known as scraper blade. So these blades, they are present near the edge of the wall so that they can scrap all the material which are sticking at the wall. Okay, then there are blades that are adjusted in height also so that there is no room for concrete to store anywhere. Okay, so in this way, there are, and once you pour the concrete from the top, once concrete mixing is done, then while opening the shaft, you can take the concrete from the bottom. Okay, so these are different types of mixers. Okay, in the last image, you can see a continuous mixture also, whereas the name suggests loading, mixing, and unloading is done continuously until the job is complete. And these such mixers, they are used for large scale projects such as dams, bridges, and construction of high rise building. Okay, so these are the different types of mixers. Now we have batched concrete and we have poured concrete in a desired concrete mixer. The next thing is about timing of mixing. Okay, how much time we need to keep it for mixing. So as per Indian standard 4925, mixing time should minimum mixing time for each batch, provided that all mixing water shall be introduced before one fourth of the mixing time has elapsed shall be 1.5 2 and 2.5 minutes for different capacities of mixture. So for different capacities of mixture, IS code has different times of mixing once all the quantity of water has been introduced. Okay. So what they say, at 0 minute you are doing dry mix. Okay. And if your mixer capacity is 2 meter cube, then your total mixing time should be 1.5 minutes. Now before one fourth of this time, so it is 90 seconds, so one fourth will be 22.5 seconds. Okay, so before 22 seconds of dry mix, okay, we need to introduce all the water that is there for the concrete, and then up till 90 minutes we need to do the mixing. So that is what IS code says. Based on the mixer capacity, there is different mixing time which is defined. Now, as per IS 2456 guideline, the overall mixing time should be at least 2 minutes. Okay, that is what IS guideline is saying. With increasing mixing time, it may result in more uniform distribution of hydration product, or we can say concrete components, resulting in higher compressive strength. So you can see here, as mixing time increases, the strength it will increase because there is more uniform mixing that is happening. Okay. However, if we prolong the mixing time for too long, it can lead to negative results also. What are these negative results? There can be over grinding of material, which can increase the proportion of fine. Suppose we are doing dry mix without water for a long time, then what will happen? Due to a friction between aggregates, there can be crushing of aggregates. Okay, which will lead to increased content of fine aggregate rather than coarse aggregate, which will disturb our mixture proportioning. And there can be excessive kneading, can also lead to segregation. Okay, so if I have a self compacting concrete, in such concrete, excessive mixing time, it can also lead to segregation in the concrete. Okay, so that's why you can see this line is taking a plateau, after which it will start to decrease again because of too much mixing time. Now just try to answer these three simple questions regarding batching and mixing of concrete. And in the meantime, if you have any doubt, you can ask. I'm sorry, I guess there was some, again, there was some network issue somewhere. I guess there was again some network halt in between. Can anyone tell me at what point that happened? In the presentation mode, it is difficult to find when the network got disturbed. Can anyone of you tell me at what point I was discussing when this network issue happened?
The dry mixing is lead to more just 2 minutes.
Okay, so we were at the end point only. So I was saying that when we do too much of mixing, then what happens in dry mix? There can be crushing of aggregates, which may lead to change in the proportions of aggregate, which is not desirable to us. And there can be segregation issues also in concrete when we do too much aggregates,
Yes,
too
yes.
much mixing. Okay, so these are the problems of too much mixing time. That's why code has given limits. Okay, at least. Okay, maximum mixing is generally less than 5 minutes. Okay, so as per Indian standard, these are the limits. Okay, which are defined. Now I was at this slide when the network went off after that. Okay, so there are some questions that I have written here for you. Just try to answer these questions based on the understanding of mixing and batching of concrete. And in the meantime, if anyone has any doubt regarding these concepts, they can ask. So what will be the answer for question number 9? In a fully automated batching plant, which system is used for precise measurement of material? Yes, the correct answer is load cells. So load cells, these are basically they how they operate. So they basically convert the mechanical force into an electrical signal. Okay, so on a pan, when we place a material, based on the force that is acting on the pan due to the material weight, that reading is converted into an electrical signal which shows us the value of that load. Okay, and such load cell, they ensure that accurate measurements are possible for cement, aggregate, waters and admixture in a automated batching plant. Question number 10: for in case of a ready mix concrete, what is the maximum time allowed between batching and placement of concrete? So in an RMC, what is the maximum time allowed between batching and pouring of concrete? Can anyone, does anyone has any idea? So this is more related to one clause in IS code. So there are a lot of IS codes that are present for different concrete types, okay, and different condition. So this question comes from IS 14926. Okay, 49. Yes, IS 4926 for ready mix concrete. The time between introduction of mixing shall not be exceed 90 minutes. Yes, the correct answer is 90 minutes. Okay, so this is present in clause, one of the clause of IS 4926. Okay, maximum time allowed between max batching and placement is 90 minutes, provided that temperature and transit conditions are controlled. Okay, in hot weather, this time may be removed, may be reduced to prevent premature setting. Okay, so this 90 minutes is given for a controlled temperature and transit condition. Okay, in cold hot weather you can even reduce this time, because in hot weather the reaction kinetics are fast. The hardening of concrete or the setting of concrete will be accelerated, so in such cases you may need to reduce this time also. And such condition, it helps us to define whether an RMC is able to deliver the concrete to a site properly or not. Okay, based on the location of RMC and based on the location where the concrete needs to be poured. Question number 11. What is the primary advantage of using a twin shaft mixer over a drum mixer? Okay, so I will tell you what twin shaft mixer is. Okay, so in twin shaft mixer, what happens? There is a container and there are two shafts which rotates in anti-clockwise direction. Okay, and we pour the material from the top. Okay, and so materials is getting mixed in the anti-clockwise direction, and once the mixing is done, we remove the blade from the bottom and we collect the material at the bottom. Okay, so this is known as a twin shaft mixer. There are two shafts which are rotating and which are mixing the material. So what is the primary advantage of such twin shaft mixer over a drum mixer? Yes, the correct answer is faster mixing time and uniformity. Why? Because such mixers, they can mix the material fast compared to a drum mixer where we need to tilt or we need to rotate the drum for pouring and for removing the material. Here we are pouring from the top, mixing is happening, we are removing from the bottom. And they also ensure better homogeneity compared to a drum mixer. Okay, because there is gravity which is governing the flow of material downwards, then we are again lifting the material, it is more uniform in terms of mixing. And such mixing they are used for high performance concrete where efficiency in blending of material is important. Okay, now question number 12, in high performance concrete which factors has the most significant impact on mixing efficiency? Can anyone tell me? For high performance concrete, which one of the following factor will have the most significant impact on mixing efficiency? I am saying. Anyone, any guesses for question number 12? Yes, sequence of material adding. Okay. How this is correct? Because for high performance concrete, the order in which we are adding the material, it is very important because it ensures that there is proper dispersion of cement, admixtures and aggregates. Okay, incorrect sequence it may lead to poor workability, inadequate mixing and inefficient hydration. Like one example I can give you, suppose in a mix we have to add silica fume. Now in dry state, suppose we added aggregate and then we added silica fume, so then in such cases what will happen during mixing, the silica fume it will settle down because it is very fine and there are big voids between aggregates. Okay, so that's why what we do, we first add coarse aggregate, then we add fine aggregates, then we add cement, and then with water we add silica fume so that there is no segregation between different components. Okay, they are all mixed thoroughly, and in such cases that's why sequence of material adding becomes important. Question number 13, what is the primary purpose of a retention period in a concrete mixing cycle? Okay, so generally there is like, so for some special concretes we talk about retention period, we stop the mixing for a small while and then we again start the mixing. So what can be the purpose of that retention period? Can you tell me the reason why B is the correct option? Like why sufficient time is required for chemical admixtures? The answer is correct B, but why we need to have sufficient time for chemical admixtures? Okay, the reason is it allows the chemical admixtures, especially superplasticizers, to fully disperse and react. Okay, with the cementitious particle before it is discharged. So, and that's why we need to have a little retention period so that whatever workability we are getting, it is the true workability of the system. Okay, so generally what we do when we add SP, we do a mixing and then we stop for a while, like 10 seconds, 20 seconds, and then we again do the mixing. So in this way we get a real idea of what is the flowability of the concrete, because it gives the SP enough time to disperse and react with the cementitious material and show the dispersion behavior. Question number 14. Which mixing method is more suitable for ultra high performance concrete? Drum mixer or a pan mixer? Which is more suitable? Yes, the correct answer is B. Okay, how? Because in pan mixer we have seen that there is shear action. Okay, there is rubbing between as the aggregate as the material is rotating. There is shearing that is happening in the material. Now, when we talk about ultra high performance concrete, we need intense shearing so that there is proper blend of fine powders, fibers, and admixtures that are there in concrete. And this intense shearing comes in pan mixture because it provides necessary sharing to and necessary sharing due to its blades and scrapers to disperse the material properly and make a homogeneous mixture compared to a drum mixer where shearing may not be that effective and there may not be homogeneity in the mix, which is critical for a ultra high performance concrete. Okay, I hope everyone are clear with all the questions that we have discussed today. So this was it for today's session. We first talked about ACI 211 code of mixture design. Then we compared IS DOE method and ACI code. Then we talked about different mixture design based on particle packing and rheology of concrete. And finally, we talked about batching of concrete and mixing of concrete and effect of mixing time on concrete performance. So this was all for today. Thank you. Now, if anyone has any doubt regarding the session or any question, you can ask.